Let's begin. Our next speaker this morning is Visu Makam.
Thank you. Today I'm going to be talking about a paper that I've written with Ankit, Rafael, and Avi. And this is going to be about barriers for rank methods. And it's a generalization of a previous result that Ankit, Rafael, and Avi had with Klim, Ephraim, and Co. And the issues that we have are going to be, in generalizing, are going to be a bit more algebraic. And so let me tell you why we're even interested in this notion of tensor rank. So if you have good enough lower bounds for tensor rank, then this will give you Vp not equal to Vnp. I hope I'm not lying. And this is by result of run-ras. Okay? Now, what is the state of art? The state of art is that if you take a 3 tensor, then most of them will have a lower bound in tensor rank of a quadratic lower bound, but the best explicit lower bound we know is about 2n. Okay? I will define some of these things, but I just want to show you the state of art. And for some reason, we don't know how to get from this 2n to something quadratic. Okay? And most lower bounds came from these things that I would like to call lifting techniques or rank methods. And what they did was they would take lower bounds and matrix rank and try to lift them to higher order tensors. Okay? And the result that Ankit, Rafael, and Avi proved with Klim was that no matter how smart you are in trying to lift matrix rank, you will never get any non-trivial lower bounds. And non-trivial here means there's some obvious lower bounds, and you can only improve them up to some constant. Just like in the case of 3 tensors, it's very easy to prove a lower bound of n, which is the local dimension. But okay, you can get up to 2 times n, but you can't get more than 6 times n. Okay? So that's the state of art there. Now what we're trying to do is we're trying to say, okay, maybe lifting matrix lower bounds is hard, but let's say somebody gave you 3 tensor lower bounds as a black box. How much further could you get? Okay? So you have some lower order tensors, you have lower bounds for these, and then you try to lift them to higher order tensors. How far could you possibly get? And we prove stringent barriers to such techniques. There's an obvious way of lifting a lower bound, a very trivial way, and whatever you get, doesn't matter how much more creative you are, you will only be able to improve yourself by a constant. Okay? So for example, if I consider 4 tensors, then most of them have a cubic lower bound, and to prove n squared is trivial. Okay? And so the previous result that they had said that if you're trying to lift matrix rank lower bounds, then you will not be able to get anything super quadratic. And as part of our result, we say even if somebody told you how to prove 3 tensor lower bounds, you will still not be able to prove anything super quadratic for 4 tensors. Okay? The constants will change though. Okay? So I just wanted to look at the numbers, and I don't want to lie too much, so I've suppressed all the constants here. And if I'm trying to lift matrix rank lower bounds to 3 tensors, then so I have this table, and I want to point out 2 things. I want to point out the things in red, which says for 4 tensors, whether you try to lift matrix rank or 3 tensor rank, you're only going to be able to do quadratic. But for 5 tensors, for example, if you try to lift from matrix rank, you'll get quadratic. If you try to lift from 3 tensors, you will get cubic, although the best is n to the 4. So there's a sort of gradation as to how far you can get. But this gradation is going to be very obvious. I mean, there's a very obvious way to get a cubic lower bound from 3 tensors for 5 tensors. Okay, and I will sort of explain this to you. So to begin with, I want to tell you all about matrix rank, but in a way that you may not entirely see directly, but you should be able to figure this out. The rank of a matrix, I want to say, is the smallest number such that you have R rank 1 matrices that you add up to get your matrix. Okay? Once you have this, I want to recast this in slightly more abstract language. I want to call the set of simples the rank 1 matrices. And I want to say that matrix rank is the additive complexity with respect to the set of simples. So if you assume that rank 1 matrices are somehow easy to compute, and you want to understand what the rank of a matrix is, it's about how many of these you need to add up to get your matrix. Okay? And this is just a general definition that goes here. If you just start with any subset that you think of as simples, and you want rank with respect to the subset, for any point in your vector space, you just say, okay, what is the smallest number of these simples that I have to add up to get to this point? Okay? And this is the way I want to view tensor rank, which you might think of as higher dimensional matrices. So let's say I'm looking at k tensors whose local dimension is n, which I will denote by 10, n, k. I want to talk about what the set of simples are. The set of simples are what are called rank 1 tensors, or you might think of them as pure tensors. And if you like to think of tensors in terms of polynomials, this is probably, okay, maybe I don't know the terminology there. And the tensor rank is going to be the smallest number of rank 1 tensors you need to add up to get to the required tensor that you're starting with. Okay? Now, I want to now talk about a paradigm for lower bounds on S rank or rank S, whatever you want to call it, on any additive complexity that you like. Okay? And the paradigm is you start with a subadditive function. A function is subadditive if it takes, if the value it takes on V1 plus V2 is smaller than the value it takes on V1 plus the value it takes on V2. Okay? And the reason we do this is this. We say, okay, let's figure out what the maximum possible value this subadditive function takes on the set of simples. Let me just call that A, and that's what A will refer to for most of this talk. Then you pick any other point that has maybe, that has some sort of additive complexity, and you decide, and you want to understand what this subadditive measure takes on this point. And because you could write V as a sum of simples, and it's subadditive, it's going to be, the subadditive measure will take at most A times the number of simples in your decomposition. Right? Now I just rearrange it, and I use that to give you a lower bound on the rank. Okay? Now I'm just going to give you a slight definition. For any subset of my vector space, I will write mu of t to denote the maximum possible value the subadditive measure takes. And I want to make this definition, which I call potency. So mu is a subadditive measure. I've told you how to gain lower bounds from this. I want to say the potency is the maximum possible lower bound you can get by such a subadditive measure. And it's going to be the maximum value this subadditive measure takes on any point divided by the maximum value it takes on the set of simples. Okay? And what we're going to do is, in this language, I'm going to tell you that most of these rank methods or lifting techniques have pretty bad potency. So let me give you one of these lifting techniques or rank methods in a very specific example. And you will see none of these numbers are particularly important. So I'm going to try and take 9 tensors and reduce them down to 3 tensors. But how? I'm just going to group 3 tensor factors at once. Okay? So that's a linear map that takes 9 tensors of local dimension n to 3 tensors of local dimension n cube. And here's a subadditive measure. It is you push forward under this map. So you take a tensor, you take a 9 tensor, you push it forward. Now you look at it as a 3 tensor and take its tensor rank. This is a subadditive measure. Okay? And I am going to confuse this linear map with the corresponding subadditive measure all the time. And so what happens to a simple tensor? So a rank 1 tensor will continue to be a rank 1 tensor under this map. Right? So the subadditive measure will take the value 1 on every rank 1 tensor, which means that on the set of simples it takes the value 1. But on a generic tensor, on most tensors, what does it go? So this map is surjective. And what's the maximum tensor rank you can have on a 3 tensor of local dimension n cube is something I already told you is going to be quadratic in the local dimension. Quadratic in n cube is n to the 6. Okay? So this tells me that the potency is going to be big O of n to the 6. Okay? So, and this was a very, very silly way of lifting a lower bound on 3 tensors to a lower bound on 9 tensors. Okay? Now I'm going to tell you the theorem in this very special case. It tells you that no matter what kind of linear map you took from 9 tensors to 3 tensors, and here I've not specified m. M could be anything. It could be really, really large compared to n. Okay? Its potency is only going to be big O of n to the 6. The 2 constants are slightly different, but you cannot do anything better than n to the 6. Okay? And there's nothing special about 3 or 9 or anything. This is just true for any d and d prime. So if you try to lift from d tensors to d prime tensors, there's an obvious way to do it, and no matter how creative you get with the map, you will not be able to do any better. Okay. So the main technical statement that we need is going to be very algebraic in nature, but it sounds extremely elementary. So we start with a setup where you have 2 polynomial maps, and what's the only thing about these 2 polynomial maps is that their images, the codomains are the same, So I put a capital N to signify that you want to think of this as a large vector space, and little m and little n to be something slightly smaller. And if you have two such polynomial maps, and all I'm asking for is that the image of L is contained in the image of M. Okay? Then I claim that you have a very symbolic statement. Then I say if you plug in variables z1 to zm into L, then you will be able to write it as m of, and you will be able to plug in power series around some point. Okay? Here's an example. It's going to be a very silly example. L is going to be the map from complex numbers to complex numbers that goes from x to x squared. Okay? M is going to be the map from the complex numbers to complex numbers, which is the identity. Okay? Clearly, the image of L is contained in the image of M. But what would this power series be in that case? In this case, the power series would be square root of x. Right? Did I get that wrong? No, I got that wrong. I have to switch L and M. Sorry. L is the identity map. M is the squaring map. So if I have to write L in terms of M, I have to start with the square root. Okay? And this square root you can write as a power series. You can't write as a power series around 0, but you can write as a power series on some other point. Okay? And that's the phenomenon that I'm trying to capture, and we want to capture it in this complete generality. And the proof of this is not obvious. For a long time, I tried to do this by complex analysis or some sort of elementary use of the implicit function theorem, and I was not able to do it. And the only way I was able to do it was to just go through algebraic geometry, okay? Which I will not present to you here, but let me try and tell you how this fits our setup. Okay? So the way this fits our setup, and I will simply describe for you what L and M are in our particular setting, and then we can see what goes on. So to begin with, I'm going to tell you that you can parameterize rank 1 tensors by a vector space. And the way to parameterize it is just the natural way of how you define a rank 1 tensor. So if you have n vectors and then you just tensor all of them together, you get a rank 1 tensor, right? And this allows me to parameterize them. And the image of this particular map psi that I put up is going to be precisely the set of rank 1 tensors. Now suppose you had some linear map from 9 tensors to 3 tensors, with the property that rank 1 tensors are mapped to rank at most a tensors. Then I will take my map to be the composition of the two. Okay? And what is the composition of the two going to have? It's going to have the property that the image of L is contained in rank at most a tensors. Okay? Now, what's the main application I have for this is, for M, I'm going to take a parameterization of rank a tensors. I told you how to parameterize rank 1 tensors, right? So how do you parameterize rank a tensors? You take the same parameterization a times and then add them up. Okay, so I won't write down the formula for this. And so what the main technical statement gives you is that you have a symbolic decomposition. And in this symbolic decomposition, you get a bunch of power series. Okay? What I'm going to do with this power series is going to be very similar to what they did for the case of lifting matrix rank. And I'm going to pull out a bunch of subspaces. What I'm going to pull out is I'm going to pull out a bunch of subspaces so that the image of L is contained in something that looks like this. Okay? And the point about the image of L being contained in something like this is that it will tell me that the image of phi, which was my linear map from 9 tensors to 3 tensors, will also be contained in this subspace. And this will follow by linearity, right? If all the rank 1 tensors land up in such a subspace, then no matter what you add, you stay within the subspace. Okay? You add them up, you stay within a subspace, and that's a crucial part of a subspace. It's closed under addition. And now the point is, anything in the subspace, you will be able to upper bound its tensor rank if you just know the dimensions of U1, U2, V1, V2, W1, W2. Okay? For example, if I look at something inside U1 tensor, U2 tensor, Cm, I claim everything has tensor rank at most dimension of U1 times dimension of U2, no matter which one you pick. Okay? So from this power series, I will pull out certain subspaces that look like this, that allow me to show the image is contained in a subspace like this. And for a subspace like this, I know an upper bound on the tensor rank of anything in there. And so you just count it, and this will give you the required result that you want. Okay? I cannot tell you how to pull out these subspaces because it's a bit complicated, But this is the crux of it. So here are some future directions. What techniques do we have to go beyond these barriers? And so what I'm trying to tell you in this talk is not necessarily how good my result is, but the fact that we're stuck with these rank methods, and this is almost the only thing that we really know how to prove lower bounds in arithmetic complexity. And so how do we go beyond this? We need to find other ideas. One of these ideas seems to be occurrence and multiplicity obstructions from GCT, but these are ridiculously hard. These are not, these are very, very difficult. In comparison to rank methods, this is a much harder technique to even try and implement. Okay? So what other ideas do we have? Another thing that I want to tell you is that, yes, we've proved barriers. So we didn't just prove barriers for tensor rank. We could also do it for warring rank. We could also do it for a bunch of other things. You can add the word border rank involved, and it all just works out with a little bit more tweaking of the technique. Okay? But at the same time, so another thing about this particular technique is that you could probably just do it for any two particular arithmetic models. If you try to lift from one arithmetic model to another one, you would be able to just run this technique. You will find some barrier. The question is how meaningful it is. And in some cases, it's not. For example, for depth first circuits, it's not meaningful enough yet. For this notion where you take sums of powers of low degree polynomials, we still don't get good enough barriers yet. Although we should expect them, because we should still expect that rank methods should not solve VP versus VNP. And the question is how to get there, how to prove those barriers. Another thing that I find personally very interesting is this particular main technical statement I defined for you over the complex numbers. It holds true in characteristic 0. I don't know how to prove this in positive characteristic. It's not true in positive characteristic the way I've stated it. And it's interesting how to work around it. And the reason it's not true is something like x to the 1 over p does not have a power series. Okay? And here's a question that I like, and I have not found an answer to, and Rafael promises me an answer, but I stopped believing him a while ago, so I have this, in this main technical lemma, I write L in terms of M with some power series in there. What is the complexity of these power series? Can you compute them with small circuits? Are the coefficients small, big, what? Is there something that you can say about it? And this, I hope, is a good question for this audience. And I will end there.
Got quite a bit of time for questions. Yes.
Why would you believe rank methods should not separate VP?
They're too simple. This is a very personal opinion. I think it's too simple the way, it's not.
Are there any other questions? In that case, thank you.